today we're learning about graphs. A lot of what you're going to go through today is just going to be lots of definitions. And because there will be lots of definitions, there is not a lot of benefit in having me write all the definitions on the screen when they're in the text. So I'm going to give a couple of examples of graphs, and then I'll be going over to zyBook and commenting on the material there. And this just avoids the need to write down definition after definition, which is not a very productive use of time. So graphs are a way of representing problems or structures that are naturally discrete. And this means things like looking at a highway network. So if we think about the main roads around the Boston area, here we have Lowell. There's some main highway routes that you might take if you're driving near Boston or from Lowell. And these have certain drive times. So you might have something like this. And here, the points represent cities. The lines connecting them represent major highways, and the numbers represent drive time. And I left out a few spots there. So we've taken a problem, and it is naturally discrete because where the highways meet are natural points to be measuring from. And a few things that you can observe from this particular one is that the way I've drawn it, there's no sense of one-way roads. If we were looking at rush hour, I might have a situation where I want to represent different drive times in different directions. So it might be 10 minutes in one direction and 20 minutes in the other. So we call that situation a directed graph, and the first one undirected. So undirected, we have lines without orientation. Directed, we have orientations. And if we added numbers to the edges, the numbers might differ in the different directions. We can also look at something like friendship. So we might have some friends. Maybe Alice knows Bob, but does not know Kathy. And Bob might know Ed and Kathy. So we might have something like this. And this tells us, if we look at these 5 people, who is friends with whom. It looks like everybody likes Bob, and the other people seem to be split up into sort of 2 cliques. Now, sometimes books will talk about an acquaintanceship graph, and acquaintanceship graph might be slightly different. Usually, friendship is mutual. If Alice and Bob are friends, Bob would agree that they're friends. Acquaintanceship can have directions because Alice might say, well, I know Bob, but everybody knows Bob, and so he doesn't know Alice. So in an acquaintanceship graph, we might have arrows here to represent the fact that Alice knows Bob, but that is not returned. And you'll notice in this figure, I did not put numbers on the edges. So depending on the context, we might have numbers, we might not. We might have arrows, we might not. And yeah. If you think back to when we were talking about relations, we also had graphs that had properties like loops. So that's another example of a graph, but something has changed here with that loop. If I was talking about main roads between cities, we might even have more than one way to get between them. So for example, if you drive from Boston to Providence, along long areas of there you have multiple routes to choose from. So you might represent that as a doubled up edge. So depending on the context, we have different names that we use. When we have a loop, we call it a pseudograph. When edges are repeated, we call it a multigraph. When you have no loops, no repeated edges, no directions, we call it a simple graph. And you can find these definitions written down in the text. And we will look at the text shortly. When we have directions, as I wrote up above here, we call it a directed graph. Now this particular one, I only listed some of the edges, but you might be tempted to call this a multigraph because you see two edges between L and A. So you actually don't have double-depth edges because they were arrows. There was a single arrow from Lowell to Andover and a single arrow from Andover to Lowell in this figure. So this is not a multigraph, even though it appears that the edge is doubled up. And then I mentioned here with the highway one, undirected graph. So undirected again meant no arrows. And you can combine these. Sometimes you'll see things like a directed multigraph or other combinations. But for the most part, we'll only be concerned with the basic concept. Do you know what a simple graph is? Do you know what a directed graph is? Do you know what a multigraph means? And in each case, there's a single thing to focus on. A simple graph, no arrows, no loops, no doubled edges. Just everything is one edge at most. Pseudograph, you have a loop somewhere. Multigraph, you've doubled up some edges. Directed graph, you have some arrows. Undirected graph, no arrows. And when we put these numbers, then we call that a weighted graph. And if you look around online, unfortunately our book doesn't have many examples, but if you look online, you can find a lot more examples like this. One that we're going to look at during the last week of class is the web graph. And the web graph is a representation of either the whole internet or some part of the internet. You put a point for each web page, and then you put an arrow between two pages if the first page has a link to the second page. So you might expect that Wikipedia, for example, has a lot of links to it and not a lot coming out. So lots of arrows point to Wikipedia. The only ones pointing out are usually based on the reference page. Not many pages would point to, say, my faculty page. So my faculty page would be kind of isolated, whereas Wikipedia would be the center of attention on the web graph. So at the end, the last week, we'll talk about how the early Google worked. And it turns out that it is related to a directed graph. So let me switch now to the SciBook. Like I said, this way I can avoid writing down 100 definitions. So you should be seeing our text on screen here. I went over some of the main terms, like undirected graph. Looking down here, you see a few other terms in bold. We're not going to worry about finite. Just means there aren't infinitely many points. The points are often called vertices. The lines connecting the points are called edges. I'm not sure why a vertex is in bold, but an edge is not. But in the figure right here, A, B, C, D, E are the vertices, and the edges are represented by pairs of elements. For example, A and B are connected to each other. So if you look down at the set E, you see AB. A is connected to C, so we see AC. A is not connected to D, so AD is not listed in that set. Now, one thing to notice here is that the edges were written using curly brackets. We've seen curly brackets before. You use those for sets. So what this means is that the order doesn't matter. In a set, the order didn't matter. And in an edge that is not an arrow, the order doesn't matter. We also saw something before where order mattered, and that was the Cartesian product. In the Cartesian product, you use parentheses. So when we need to do directed edges, we will put parentheses. And you can see that in the fine print down here that's mentioned. When we want to do undirected edges, we use curly brackets because there's no direction. And they're illustrating that in this figure. Sometimes we count vertices and edges. So in this figure, each of those, well, the graph on the left has 5 vertices. If we wanted to count edges, the graph on the left had 3 edges. And when we want to count the numbers, we'll use the cardinality notation we learned for sets, which means absolute value sign. So on the figure 1413, if I put the absolute value of V, capital V, I would be asking how many vertices are there? And the answer would be 5. If I put the absolute value of E, that would be the number of edges, which is 3. And you don't read it absolute value, you read it as cardinality. They're adding a little bit of terminology here. If you've doubled up an edge, you can call it a parallel edge. But it's also common to just call it a repeated edge or a doubled up edge. A loop, I guess, could be called a self loop, but oftentimes we don't bother with the word self. As I mentioned before, a simple graph doesn't have doubled up edges, and it doesn't have directions, and it doesn't have repeated edges. If 2 points are next to each other, then they're called adjacent. So in this figure, A is adjacent to B, but A is not adjacent to E. So physically, when you look at the drawing, A looks close to E. But if you think in terms of edges, A is not that close to E. To get from A to E, you have to go A to B to E. So when you have that in-between point, it is no longer adjacent. The degree of a vertex is the number of edges at that point. So in this figure, A has 2 edges, so we call it degree 2. B has 3 edges, so that's degree 3. In this figure, there are 3 vertices of degree 2 and 2 vertices of degree 3. There's a few other terms here. I'm going to skip them, but you can certainly read them if you want. So if we have a big graph, let's say that we think about the friendship example. If I have a graph that shows who is friends with whom, I might want to zoom in on some particular subset. For example, if I had the friendship graph of every student at UML, that would be pretty big. And somebody might come along and ask something about a particular subset, like, do most computer engineering students know each other? Well, in that case, I would limit myself to Comp E students. So when you limit yourself to a small part of a bigger figure, that is called a subgraph. So a subgraph usually has some edges or points thrown out. Technically, it doesn't have to, though. So I could look at the computer engineering students and throw out everyone else. that would give me a subgraph. And various examples in here. So when you go through and do the exercises, you'll get plenty of practice with these. So before I get to this theorem, I'm going to jump ahead to some common graphs. So we've seen the definition, we've seen what a graph is, and now let's look at some common examples. So common type of graph is a cycle. A cycle means the points go in a circle. So looking at figure 14.18, on the right-hand side, you have a cycle, and that cycle has 7 points. So we call this a cycle of length 7. You might also say, well, what if I'm looking at, say, friendship, and I want to find a group of friends who all know each other? That might mean, for example, that there are 6 people, and all of those 6 are buddies with everyone else in that group. Well, in that case, if I was to draw their friendship graph, every point would be connected to every other point, and that is called a complete graph. The letter K is used for it, probably because C is already used up by cycle. So on this figure here, you have a complete graph on 6 vertices, called K6. I am going to skip the hypercube example, Q3. You don't need to know that for here. Now, sometimes when we look at a graph, it actually splits up into 2 groups. A common example that is used for this is figures that involve male and female. So we might want to look at something like they used to talk about the marriage graph. And in the traditional sense, a marriage graph would connect men and women. Now, this figure has a lot of edges, but a marriage graph, probably each person is connected to only 1 or 2 other people, depending on whether they're divorced or not. So we might put men on the left, women on the right, connect a man and a woman if they've been married, or dating, or whatever variation on that theme you might want. So that is called a bipartite graph. And I don't see that definition here. It will show up at some later point. So a bipartite graph, again, was where you split up into 2 groups. Notice in this figure, they have taken 3 points on the left, 4 on the right, and connected them all. So that's called the complete bipartite graph. And then the subscripts just tell us how big the 2 pieces are. So this is the complete bipartite graph with 3 vertices on one side and 4 on the other, and then all the edges possible between those 2 groups. Sometimes we call, So we're going to talk about something called matchings, not today, but in a later class. And in that case, we'll be looking at bipartite graphs. Okay, so let's talk about how to represent graphs. Now, I know that I skipped one topic before. It was a theorem. I'll be coming back to that later. I want to go through all of our definitions before we get to the more detailed stuff. Okay, so initially here, we're repeating what we saw before. Here's a graph. Underneath, you can see the vertices and the edges. Now notice that if you look at these 2 figures, they're actually the same. On the left-hand side, A, B, and C were all connected to each other. On the right-hand side, A, B, and C are all connected to each other. On the left-hand side, B, C, D, E form a cycle. On the right-hand side, B, C, D, E form a cycle. So what this is trying to show us is that you might draw two figures that look different, but they're actually the same. So when we're looking at graphs, it is important to realize that the way in which it is drawn is irrelevant. The only thing that matters is what points are connected to what other points. This might be clear when we think about the friendship graph you saw before. If I was drawing a graph showing friendship, there's no physical location of the individuals. A dot represented a person. The placement of the dot didn't mean anything. So in a friendship graph, the only thing that matters is who is friends with whom. We will learn next class about what is called isomorphism. Isomorphism is going to give us a framework to describe when two graphs are different. So if somebody gives you two graphs and they look like they might be the same, but you're not sure, isomorphism is used to check if they're the same thing. But for now, all we want to get out of this is that the way a graph is drawn doesn't matter. It just matters what connects to what. So the two graphs in 14.2.1, they're identical. So let's suppose I have a graph. We've learned that we can represent the graph in two ways. One, you draw it. Two, you list all the edges. Well, there are lots of other ways to represent graphs. One of them that we will not use in this class is the adjacency list. So adjacency list means you write a vertex and then you tell what it's connected to. In the example you see on the screen here, A connected to B and C. So row A in the adjacency list had B and C after it. B connected to A, C, and E. So row B had A, C, and E. There are cases where adjacency list is useful, probably related to coding. But for our purposes, it's not that helpful. In fact, we will use adjacencies list in a slightly different way. A more useful representation is matrices. And the reason for that is that there's lots of software that is highly optimized to deal with matrices. One example is a GPU. The graphics cards are really good at doing matrix operations quickly. So we can represent a graph as a matrix. And the way that you do that is that each vertex corresponds to a row. If the vertices were numbered, then there's kind of an obvious way to do it. In this case, they've numbered them 1, 2, 3, 4, 5. So it's natural to make the rows 1, 2, 3, 4, 5. If we think about friendship, well, people's names are not numbers, so it's a little less obvious. So if I was trying to make a matrix for a friendship graph, I would probably label the rows of the matrix to make it clear who was connected to which point. And they've done that in this figure here anyway. They've labeled them 1, 2, 3, 4, 5. The columns get the same representation. And the important part is that we will put a 1 in a row and column if there is an edge between those points. So for example, vertex 2 is connected to vertex 3. If you look at row 2, column 3, you'll see a 1 there. 3 is connected back to 2. So if we look at row 3, column 2, you'll see a 1 again. Generally, you get a diagonal symmetry here. row 2, column 3 had a 1. Row 3, column 2 had a 1. Where this will break down is when you have directed edges. So if we had arrows here, it might be a bit different. So when there's a directed graph, you need to make sure that the row is the starting point and the column is where the arrow ends. So if there were an arrow from 3 to 2, then row 3, column 2 would get the 1. If the arrow was from 2 pointing to 3, then row 2, column 3 would get the arrow. So a lot of graph operations can be done by using matrices. And that's why, like I said earlier, the matrix form of a graph can often be useful. The downside is when the graph has a lot of vertices, this can get out of hand. So if you imagine something like a web graph, even a small one, let's say I took the web graph of all pages at UML. I do not know how many pages there are, but let's say there were 1,000 of them. And that's probably very pessimistic. I'm sure that there's 10,000 pages or more. But if there were 1,000 pages at UML, and I wanted to represent how they're related to each other, I would need a matrix with 1,000 rows and 1,000 columns. Well, that's 1,000,000 entries. If there are 10,000 pages at UML, I would need 10,000 rows and 10,000 columns, which is 100 million entries. So when you have a reasonably large structure, that gets out of hand. The adjacency list is much more helpful because if there are 10,000 pages at UML, most of them only have a handful of outgoing hyperlinks. So if an average page had 10 links and there were 10,000 pages, 100,000 links is a lot less than 100 million entries in the matrix. So this is where the adjacency list might be helpful, even though I said we won't use it in this class. When we talk about the Google PageRank, that's a case where they're sort of using the adjacency list. A web graph is huge, like I discussed. If Google had to do your web searches by using massive matrices, it would take a long time. So let me backtrack at this stage and look at some earlier examples of graphs that we saw. So you'll notice that the title of the section in the book says Intro to Graphs, and see also week 9. So back in week 9, we had directed graphs and graph powers. Also some matrix multiplication, which we didn't look at. So directed graphs, lots of terminology, similar to what we've been talking about. We have vertices, we have directed edges, which are arrows, we have self-loops, and so on. One slight difference, when we talked about degree before, the degree of a vertex was how many edges were at that point. When there are directions, you need to decide whether the edges start at the point or end at the point. So in degree tells how many edges point into that point. If you look at the example on the screen here, the in degree of A is 0 because nothing points to it. The out degree of A is 2 because there are 2 arrows pointing out of it. The example right here is kind of what I was talking about with a web graph. We have a very small portion of the web 4 web pages. A parent has a blog. Well, not surprisingly, their local doctor, drug company, and academic institute do not point to that blog. However, that parent has links to those sites, depending on what they're talking about. Here it says the parent is talking about a child with an allergy. So they might have a link to their allergist. They might have a link to the drug company making the meds their kid takes. They might have links to Academy of Pediatrics talking about asthma. And if you look at this small graph, a natural question to ask would be, based on this graph, if somebody did a search for allergies, what web page should rank first? Well, using our knowledge, we might say, well, a parent, they're important to their kids, but not in general. Doctor is a bit more important. The drug company, well, they have lots of information. But an Academy of Pediatric Medicine, well, they're the most important. So intuitively, I should put the Academy of Pediatrics at the top of a search about allergies in children. We can also see this by looking at the figure. Lots of arrows point there. So everybody thinks that's a good site. I should rank it high. The drug company is the next most popular. Pediatrician has a link, and the parent goes at the bottom. So you can see that there is some intuition that tells you, based only on the graph and knowing nothing about the search that you're looking at, if I know nothing about allergies or what's going on, I can still rank the web pages just by looking at these arrows. And like I said, we'll talk a bit more about that when we look at PageRank in the last week of class. One thing that's interesting, the explanation I just gave now about how many arrows point to the page, that's what search engines used to do before Google. And if there's anyone in the class old enough to have used search engines pre-2000, then they would know that search engines were pretty bad back then. So when I looked for something in Alta Vista, for example, I could have to go down pages of links to finally find a page that I wanted. So it means I might have to go down 30 or 40 items to find one that was correct. So it's very easy to game the system if the number of links is all that matters. Yahoo was a good search engine because they were managed by humans who would manually rank everything. But Google managed to do the same thing without human involvement. So let's suppose we have a graph. And the graph in this context often involves arrows, but it doesn't have to. Then a walk is a description of moving around the graph. You start at a point, you follow arrows to get somewhere. If you look at the activity down below here, maybe I start at A, and maybe these arrows represent paths, places I can go. So there's no way to get from A to D directly, but I could go from A to B and on to D. We call that a walk. And there's a lot of terminology surrounding walk. You can find some of the terms here. And I'm not going to go into much of this because we're only going to look at a subset of graph theory topics. But the length of a walk is like the distance. If each of these edges represented 1 mile, and I asked, how far do you have to walk to get from A to D? Well, you have lots of ways to get there. But the most obvious one would be A to B, 1 mile, to D, another mile. So it's 2 miles to get from A to D. You could do something ridiculous, like go from A to B to C, backtrack, and then D. That would be 4 miles. That's not a very good way to get there, though. So the length is usually the shortest way of getting between points. As I said, there's lots more terminology. I'm going to skip this. This is just different terms about walks. So let's look at this example here. If I look at A, it has out degree 2 because 2 arrows point out of it. It has in degree 0 because no arrows point to it. This is a directed graph because we have arrows. If I start at A and I ask you the length of the shortest walk to E, there are several different ways to get there. For example, I might go A, G, C, F, E. That was 4. I might go A, B, C, F, G. Again, it took me 4 steps to get to E. But if we look carefully, we can see A, G, F, E gets there in 3. So a topic we'll talk about later is shortest paths. In this case, I found many length 4 paths from A to E, but there was a length 3 one, which is shorter. On this graph, there are 7 vertices. If we count edges, there are lots of edges.